Welcome to Weekly Physics and CSZC with Sir Danny. Today we're going to talk about electric field, the next part of our lesson in Electrostatics 1. So we're going to talk about electric field this day and how do we use electric field using basic concepts in physics and how is electric field related with Coulomb's law or electrostatic force. So first is we need to define what is electric field. An electric field is defined at any point in space as the net electric force on a charge is divided by that particular charge. So, what do we mean by this? Uh, Electric field is the the amount of force present on a charge on a certain space. Now, uh, to furtherly understand this one, to furtherly understand electric field, we need to understand also that this electric field is just an imaginary field. It is an imaginary space where the interaction of electric charges happens. Electric field is a space where the interaction of electric charges happens. So if there is an interaction of electric charges, then there is an electrostatic force present. Now, we test electric field by placing a test charge. To identify that there is an electric field, there must be a test charge present. And later on, we will see how do we test an electric field. To further understand what is an electric field, there is an illustration on how do we see electric field. And we call it as electric field line. An electric field line is a map or an illustration of the magnitude and the direction of the electric field. So I have here three illustrations that would identify or that would show an electric field. Illustration A, it shows the electric field of a positive charge, a single positive charge. So notice that there are arrows. The arrows tells us the electric field line. Arrows are used to illustrate the electric field line. Number two, there are two electric charges, two equal yet opposite charges. We call also that one as a dipole. Now, as you can see, a single positive charge and a single negative charge are present. And yet, the arrows is pointed towards the negative charge. So why is that? Okay. Why does that happen? So meaning, these two particles or charges are attracted with one another. So if it's attracted to one another, then there is an electrostatic force present. If there is an electrostatic force present, then there is an electric field. And we illustrate that field using a field line. That's why there are arrows pointed towards the negative charge. But the question is, why towards the negative charge and why not towards the positive charge? Later on. The third illustration are two equal positive charges. And notice that these two equal positive charges are repelling with each other. And notice that the lines are not meeting. The electric field lines are not meeting each other, but they are what? What happens to the line? They would just cross with one another. They are now parallel with one another. They do not intersect. Right? They do not intersect. They just meet, but they do not go together as one line. They move separately. Because these are the property. This is because of the property of an electric field, or electric field line. One of the property of electric field line that is the electric field line. If you illustrate an electric field line, it must begin from the positive charge always. and it will end on the negative charge. So if there are no electric negative charges present in the system, then there will be no electric field line present because there's nothing to be attracted to. There's nothing there's nothing to be attracted to. If you have a positive charge, the positive charge will just repel with one another, right? So the field lines are always pointed away from the positive charge and towards the negative charges. That's the first property. The second property of electric field line is that it should be the electric field line as the electric field line moves away from the positive charge, it should be perpendicular to the surface. And if it's perpendicular to the surface, it also enters the negative charge perpendicular to the surface of the electric charge. So notice that this particular electric field line, notice this one, the one on the middle, it is the electric field line is perpendicular to the surface of this positive charge here. So it moves towards this direction. It moves perpendicular to the surface of the negative charge. So it also enters on the same perpendicular surface of the charge. But that always happens. The same is true with this one. So as you notice, this one moves perpendicularly to this one. It doesn't go from this point, from this perpendicular point of the surface of the charge. It doesn't go here, but it goes here because the electric field line should get into the electric field line should enter or should be perpendicular to the surface area of our electric charge. So since these two are identical, they are spherical in nature, so they should be the same. Now, the third property is the electric field line should not start or stop in the middle. Okay? The electric field line should not stop or start in the middle between two charges. It should be from a positive and from a negative. Okay? From positive to negative. Now notice, this is the electric field line. At each point in the space, the electric field vector, excuse me, this one is tangent to the field line passing through a certain point. So what do we mean by this? So electric field is a vector quantity. So the sum of all of the points here are tangents of the electric field. So whatever will be the magnitude of this one, of the electric field at this particular point, should be the same with the magnitude of this particular point. Okay. Then so on and so forth. So it should be tangent, okay? The magnitude of this electric field here at this point is tangent to the point here. So the magnitude here, so if this is the electric field that is going straight, so this is also going here, and here, and here, and here, and here, until it reaches net electric field. I have here a simulation on electric field. So let's try to see how electric field happens or how electric field is being simulated. So I have here a charge of 1 nanocoulomb. Let's take a look on the electric field lines. The arrows are the electric field lines. Okay? Now the arrow is pointing outwards. So if I'm going to, so let's put a sensor. The sensor would tell us the direction of the electric field. So if I'm going to place it here or here and anywhere. Okay, so let's place a sensor here. Now, I'm going to add an electron or a negative charge of -1 nanocoulombs on this side. Now, what? Notice that some of the electric field lines are pointed towards the negative charge. So, what happens here? I want to remove the sensor. Here, we have here. I'll place another positive charge. Let's see what would happen. Okay. Notice that the electric field lines rep, uh, is not going with or is not pointing towards the positive one. It's always outside. If I place a negative charge here in the middle of the two, it's what happens? The electric field lines are always pointing to the negative charge. So if I'll place a negative charge here also, it's also the same. And then I'll place another one here. So let's move it on equal distances. Right. So that's what happens. So let's try to put more electric particles. So the more particles are there, the more the interaction that's going to happen. So notice, so let me restart this one. Notice that two particles would meet. Okay, there are the whatever would be the, the area that they live or the area where the electric field line would start to live, it will find the similar area on the negative charge to enter. Right? Place here, here. What's going to happen if there are two positive charges? They do not intersect with one another. But if there is a negative charge, those electric field lines would go to the negative charge. Okay, so there are two. So there is a loop here. There's also a loop here. Any questions? That is an electric field line. Now, electric fields are represented using an equation. Now, as I've said a while ago, that the electric field is always tested with respect to the test charge. Test charge is denoted as Q naught. Okay? What is the difference between a test charge and a charge? A test charge is a very small charge, just to test that there is an electric field present. So if there are unknown charged particles present, then we have our test charge to identify that there is an electric field in the system. Okay? Now, the test charge is always uh, smaller than the charge. Now, of course, there is a force present between these two. Now, electric field is denoted as capital E, which is equal to the ratio of the electrostatic force with respect to the test charge Q naught. And sometimes, using Coulomb's law, we can derive the equation using Coulomb's law to transform this into this particular equation. And how do we do that? How do we do that one? We do that using this technique. We substitute the equation, or We can play along with the equation. We have here E is equal to F all over Q naught. Now remember F is equal to, let's use a green color. F is equal to K Q Q2 R squared. Yes? Okay. Now, let us substitute this equation to F. And how do we do that? So we can write here as E is equal to K. Now we have an individual charge. We have an unknown charge Q. Yes, we have an unknown charge Q, and we want to test that this charge Q has an electric field. So we need to put a test charge Q. So since there is a test charge Q, okay, there is a test charge Q naught present from this equation. So the Q2 here would be written as Q naught. Right? Because Coulomb's law is an interaction between two charged particles. So we have an unknown charge and a test charge. So there is an interaction between the two charges. And then we can write R squared. Of course, this test charge and the other one, the unknown charge, is separated by a certain distance R. So what can we do now is that we can easily equalize the equation. We can simplify the equation by dividing Q both sides, because Q naught divided by Q naught is equal to 1. So that would leave us K Q all over the square of R. Right? Now, that is how we derive the other equation for electric field. So there are two equations that we can use. We have equation 1, this one, equation 1, and equation number 2. Okay. Now, this is how we derive the mathematical relationship of electric field. Now, let's identify or let's describe each of the variables present. Okay. Of course, F is our electrostatic force in Newton. So electric field E is has the unit of newtons per coulomb. Okay? Force per coulomb. Force per charge. Unit charge. So capital N all over C. R is distance within meters, then coulomb, charge C, and the coulomb's constant. Okay, this is capital C. Yes, Newton meter per coulomb square. Okay, now let's put the equation to the test. What is the magnitude and the direction? What is the magnitude and the direction of an electric field that exerts 2 times 10 to the negative 5 Newton upward force, okay, on a 1.75 microcoulomb charge? Now we have an upward force of 2 times 10 to the negative 5 newtons and a charge of 1.75 microcoulomb. So what equation do we need to use? Are we going to use equation 1 or equation 2? Very good. We're going to use equation number 1, which is E is equal to F all over Q naught. So what is our Q naught? 1.7 microcoulomb. So what made us say that Q naught is 1.75 microcoulomb? From the term itself, or from The unit itself, microcoulomb, that gives us the idea that it is a very small charge. Okay? Micro is times 10 to the negative 6. Okay? Now, so we have here E is equal to F with the, E is equal to F all over Q naught. So how do then we substitute all of the values? So we have 2 times 10 to the negative 5 divided by 1.75 times 10 to the negative 6. So how did we come up with 1.75 times 10 to the negative 6? So how is that even possible? So it's like this one. Remember, 1.75 microcoulombs, 1.75 microcoulombs is equal to 1.75 times 10 to the negative 6. Why? Because 1 microcoulomb is equal to 1 times 10 to the negative 6 coulombs. So let's convert 1 microcoulomb or 1.75 microcoulomb to 1 coulomb or a coulomb. So we have here 1.75 microcoulomb times 1. So in every 1 microcoulomb, we have 1 times 10 to the negative 6 coulombs. So that would give us, this one will cancel out. This one would cancel out. So we will have here 1.75 times 10 to the negative 6 coulombs. That's how we got 1.75 times 10 to the negative 6. You can also write this as 0.175, if I'm not mistaken. 175 times 10 to the negative 5 coulombs. Yes, that can be done also. Why? Because we just adjusted 1 decimal place to the left. Okay. So now going back to our equation here. So we substituted F, that's equal to 2 times 10 to the negative 5 newtons all over 1.75 times 10 to the negative 6 coulombs, or 0.175 times 10 to the negative 5 coulombs, but I'm more comfortable using this one, 1.75 times 10 to the negative 6 coulombs. So if we divide the two, that would give us 11.4 newtons per coulomb. So this is the amount of electric field present. So this is the amount of electric or of the electrostatic force applied in the field with respect to the charge or to the test charge present. 11.4 newtons per coulomb. Are there any questions? If there are no more questions, please, if there are still questions for this particular lesson, please do comment down your questions and I'm going to answer you. Thank you very much for joining me this session on electric fields. I'll see you on electric flux session.